Hey everyone, let's derive the derivative of sine of x. Now in order to do this, we first need to prove fact 1, which says that the limit as x approaches 0 of sine of x over x equals 1. This may not be obvious just by looking at it. If you looked at a graph, then it would be. But we need to prove this, and we actually prove it using the Squeeze Theorem. Now what we do is we're going to get that unit circle drawing up and running again. We're actually going to, maybe don't even the axis. So if we have our unit circle here, right, means we have radius 1. Recall that, right, if this is theta, maybe I'll prove it using theta instead of x, right, but it's just a variable name. Recall that this right here is sine of theta, that distance right there. Also recall that this right here, this distance, is by definition theta. Maybe I'll actually put theta up here a little bit. You'll see why in a sec. That's theta. And last, this is something we didn't cover in class, this right here, that length right there, is actually tangent of theta. To see this, you have to know that it's proportional to the length sine of theta. And remember that this length right here is, by definition, 1, right? Just like that length, right? Pretend that circle's perfect, right? And that this is cosine of theta, right? This length right here. So what you can see is that sine by the sort of corresponding parts of similar triangles, sine of theta over cosine of theta, right? This side divided by this side equals tangent of theta over 1, right? Or I should say this length right here, right? This length over this length over this length, right? So that's why you know it's tangent of theta, right? Because that yellow length has to be tangent of theta. Okay? So what you can see by looking at this actually is a little bit of an annoying proof to show that theta is bigger than sine of theta but less than tangent of theta. It's kind of an annoying proof. Stewart does it in the book. I'm not going to get into it. But what you can gather from this is that sine of theta is less than or equal to theta, which is less than or equal to tangent of theta, for any theta, right? I could have drawn any triangle. I could have drawn this right triangle. The same thing would have been true. Okay, now I'm going to use the imply symbol a little bit here. We're interested in sine of x over x, or sine of theta over theta. So what we're going to do is we're going to do 1 over everything. 1 over sine. 1 over theta. 1 over tangent of theta. But when you do this, you have to be a little careful. The inequalities switch. They switch directions, right? 5 is, if 5 is less than 7, then 1 over 5 is bigger than 1 over 7, right? Divide by stuff, everything switches, okay? So, we have that. Now, we're not interested really in 1 over theta. We're interested in sine of theta over theta. So, we're going to multiply all 3 sides by sine of theta. So, we're going to get sine of theta over sine of theta greater than or equal to sine of theta over theta greater than or equal to sine of theta over tangent of theta. Well, remember for a second, I think it's pretty clear that, right, sine of theta over sine of theta is just 1. Sine of theta over theta is exactly what we're looking for. And remember that tangent of theta is sine over cosine. So with a little bit of simplification, right, dividing by sine over cosine is the same as multiplying by cosine over sine. We're going to get cosine of theta, right? The sines will cancel out. Now at this point, I hope this looks a little bit familiar. since the limit as theta approaches 0 of 1 equals the limit as theta approaches 0 of cosine of theta, which is 1, by the squeeze theorem, the limit as theta approaches 0 of sine of theta over theta equals 1. Cute little application of the squeeze theorem right there. Okay, now let's remember why we did this. We did this so that we could derive the derivative of sine, and as we know, show that the derivative of sine equals cosine. Okay, let's do that. Definition of the derivative of sine, right? Just by definition, I hope we all know this, even if we couldn't necessarily get past this first step, is the limit as h approaches 0, sine of x plus h minus sine of x all over h. Now, at this point, you need to use some trig identities. We didn't go over this in class, but maybe you've seen this before in pre-calculus, maybe in trigonometry class, that sine of x plus h can be written as sine of x cosine of h plus cosine of x sine of h. That's just the addition formula for sine of a plus b, or x plus h, or for sine, you could say. Nice identity to know in this case, right? And this stuff is all over h. Okay. So I guess at this point you might notice that we do have a common factor of sine of x right there, so maybe we want to group those two together and maybe pull out that sine of x if we can. So maybe what I'll do is I'll say this is equal to sine of x times the limit as h approaches 0 of cosine of h minus 1, right? When you factor sine out of that, you just get 1 all over h. Plus, I'm going to use limit laws right here, plus the limit as h approaches 0 of... Actually, I guess I could go even further, take out the cosine of x and have the limit as h approaches 0 of sine of h over h. There's a lot of steps right there, right? I broke up this term and this term, and then split the limit, right, using limit laws. I also factored out this and this, right, the sine of x parts. Okay, so there's a lot of simplification in that one step. See if you can follow. But we know that this limit right here goes to 1, right? That's what we just proved. So maybe what we have to show is that this whole thing is 0, which I guess means showing that this limit is 0. And this is a little bit annoying, unfortunately, because the limit as h approaches 0 of cosine of h minus 1 over h is 0 over 0. So we have to do a little bit of work. It's an indeterminate form. But what we can do, I'm not sure how obvious it is we can multiply by the conjugate. Cosine of h plus 1 over cosine of h plus 1. Plus all this other stuff. Right? I'll just say, maybe I'll use a highlighter in this case, right? I'll use pink, let's say. Ooh, that doesn't, I'll use yellow. Pink obscures it a little too much, right? That was by fact 1. Okay. All right, great. Well, what's this going to give us? This is going to give us sine of x times the limit as h approaches 0 of cosine squared of h minus 1 all over h times cosine of h plus 1. And then I guess over here we've got plus cosine of x. All right, well, why is this useful? Well, remember that special identity, sine squared plus cosine squared is 1, right? Well, I guess that means that 1 minus cosine squared is sine squared, or cosine squared minus 1 is negative sine squared. And I guess we can be a little creative about breaking this up, right? Because we're still getting a 0 over 0. But maybe if we use some limit laws and, split this up into sine of h over h. Hopefully that looks familiar. And then here we have negative sine of h over this stuff. Just draw that out. We see, actually, don't forget your cosine of x. We'll see that we get sine of x times 1. Again, hopefully we notice that. Fact 1 is once again appearing. Times, now we can actually take this limit, right? The top is 0, right? Negative sine of h, as h approaches 0, that's just negative 0 or 0. And the bottom, cosine of 0 is 1, so we actually get 2 on the bottom. So our answer is just cosine of x. And that's how you show that the derivative of sine of x is cosine of x. Took us only 2 pages to do it.